today. Yeah. Yes, we are now live on YouTube. Welcome everybody to this evening of Learning Physics with Conceptual and Problem-Based Approach, organized by the National Academy of Sciences, NASI, India, Delhi chapter, an 11-week course which started on the 27th of July 2020, every evening from 5 to 8 p.m. And today we have a new speaker with us to continue our subject of atomic physics. That is Professor Hashmi from the Department of Physics and Astrophysics, University of Delhi. And the second speaker would be for thermal physics, Dr. Seema Gupta. So now the introductory slide of Professor Hashmi, please. Yes, it's a pleasure for me to introduce Professor Hashmi to the audience and the attendees and the participants. Professor Hashmi is a professor in the Department of Physics and Astrophysics, and after receiving his PhD degree in 1988 from Banaras Hindu University, Varanasi. His research work involves fabrication of magnesium and sodium rechargeable batteries using gel polymer electrolytes, development of solid state and flexible supercapacitors based on carbonaceous materials and conducting polymer electrodes, development of thermally and electrochemically stable polymer electrolytes, and their application in energy storage devices. He is one of the members of Expert Committee for Project Evaluation of Young Scientists and Inspire Fellowship Evaluation of Physical Sciences, SERB, DST, New Delhi. He has published several research papers in various international journals and authored 2 books on the topics of materials and devices. He is also collaboration with prestigious national and international institutes. Welcome, sir. I'm very grateful to you that you have agreed to give us a series of lectures on atomic physics. And this is a very, very important subject. So we are really pleased that you have agreed for the same.
Yeah.
Sir, am I audible? Yeah.
Yeah, thank you very much, Dr. Punita, for your nice introduction. So I think that several participants have already joined.
Yes,
around
sir.
43. And
Yes, sir.
how many of them are students? I'm not sure, but
No, sir. All are 99.99% are students, and 0.01% is the organizing committee members which are sitting to manage the meeting.
Yeah, okay, no problem. So nice of you.
Sir,
So
please switch on your video for 1 minute so that the students know whom they are speaking with. And if the bandwidth, if you're using Wi-Fi, then you can keep your video on and share your screen. That way your face will be visible to the students along with the lecture.
okay, so I have already on my video. I'm not sure that it is working or not, but
It's not working, sir. I can't
it
see
is
you.
not working. Yeah, but my video is on. Somewhere I have to make it allowed or not allowed. Where is that? Yeah, on. नहीं, video pause हो गया.
Yeah, now, yes, sir. Yes, sir. Now we can see you.
Okay.
Yes, sir. We can now see you.
Okay.
Thank you so much, sir.
Yeah.
I request you to now share your screen and deliver your talk.
Okay, fine.
Thank you. Sir, you have to share the screen at the bottom.
I'm doing it.
Yes, sir. There is a delay in pressing buttons, and meanwhile, attendees, please be careful that your mic is not unmuted. It should be on mute. So now you have to just do the slideshow. Press at slideshow. Yes, perfect, sir.
Yeah.
Yes, sir, perfect. And students, if you have questions, you will write them in the chat box and we shall take them at the end of the session. So if you have queries, write down in the chat box. Yeah.
Yeah. So
Please
if the
continue.
students have some minor problems during the talk and lecture, then they can interfere me and I'll definitely answer briefly. But I would like to answer their other questions at the last or maybe they can contact me on my email, which is given here. I will definitely write their the reply. Yeah.
Thank you so much,
So,
sir. Thank you so much.
okay. Yeah. So should I start?
Yes, sir. Please start.
Yeah. Well, so welcome all the students to my this class of atomic physics. Um, so it is not a new topic for you because you are already aware about the atomic physics during your PhD classes, and very recently Professor Kundu has taken your several classes on this topic. So I am going to uh, give you some idea of atomic physics once again. And you know that if different teachers are teaching you the same subject, sometimes you find difference in the explanation and in various aspects. So I would, I'm sure, I'm confident that whatever I'm going to discuss with you, it will be very useful to you. So I will start with very basic concepts of atomic physics. So for that purpose, let me show first to you that um, the topics what actually because of some reason I'm taking your only three classes and three classes of 1.5 hours. So I'll be for total 4.5 hours with you today, 1.5 hours. So in during this period of 4.5 hours, I would uh, try to cover some important aspects. Definitely, it's a very vast subject, so it cannot be covered in a very short period of time. But I will start with something that it will be useful to you in your studies further. So I would start with a very brief introduction of the atomic physics and historical background and something very interesting in the inventions what has happened in the physics, atomic physics. And then I'll proceed to a specific topic, taking the example of one electron atoms. And I'll directly start from the fine structure, giving some brief about the initial problems, and then go to the fine structure. And in that, you know that during the fine structure analysis, there are three important aspects. That is the different types of corrections in Hamiltonian, what I will discuss with you. That is the relativistic kinetic energy correction and the correction due to spin orbit interaction, and then some Darwin terms because of the potential energy correction. Then you may have seen several in spectroscopy, several energy lines, sometimes in photographic plate or in the computer screen. And then this is because of this transition. So you know that in when electron jumps from one level to the other level, all the energy transitions are not allowed. So what are the conditions? What are the selection rules? I will discuss about it. Some very important aspect is the some discrepancies were found, and it was explained by Lamb, and that Lamb shift I shall discuss. And then you see that in the fine structure of the spectral lines and the fine structure, there is intensity of the line is also very important. So I will try to uh, touch that also. And then in the middle, somewhere wherever it is required, I will try to do some numerical problems discussed with you. And then at the last, I would give some numerical problems to you as a tutorial, so that you can do at home. Sometimes you find time, and then you can discuss with me through the email, and I'll definitely help you. Yeah. So the book I would like to refer to you, these are the books what generally I follow. But the main book what I follow is the Physics of Atoms and Molecules. You may definitely knowing it. It's a very famous book. That is the Brasden and Zochen Physics of Atoms and Molecules. And the second book is also very good. It is Hirokok and User's book of Atomic and Molecular Physics. But this book is rarely available in libraries, uh, but it is available in Delhi University. Well, and the third book is very popular. It is by Raj Kumar, but I'm not suggesting you to follow it up throughout, but it can be used as a reference book sometimes for doing some numerical problems and the problems oriented questions. Okay, so with this brief introductory things related to your preparation, that how to proceed, I would like to start from the very basic of the atomic physics. That atomic physics means that atomic spectra, I mean to say. So this is a very important field which is called spectroscopy, and this is the field. Actually, it is the experimental and theoretical research, and this is the one of the field which always always go on parallel, like experimental inventions and theoretical models and theoretical research. Always it has gone very parallel, where experimental needs were there, theoretical models were there to explain them. So it was almost parallel. So it was a very interesting physics, in the which is called modern physics. It was that, and so scopy is the field in which it is the research in which knowledge about the physical nature of things on the Earth or interstellar spaces and sun and star can easily be characterized and found, that what are the constituent materials there. Uh, uh, the spectroscopy is a uh, powerful field to know that. So its first beginning was started in 1666, when Newton discovered one phenomena, that from the prism the light can be dispersed. You can see from here the picture that Newton was the first scientist who resolved the white light into separate colors by diffraction with a prism. And so from there the spectroscopy started. And you know that after a very long time, then even 100 years, no development was there this field. But in 1752, one scientist, uh, Melville, he showed first time that from the incandescent gas which is burning of any element which is burning, it is able to give you a discrete frequencies which are called the emission lines. So not the continuous, discrete frequencies from any, and different incandescent gases of elements give different emission lines. So this has become something very interesting. And one of the another interesting thing was found, discovered that some white light, if you incident onto this burning gases, that is incandescent gases, then some of the frequencies are absorbed, and on the plate some absorption lines were observed. So emission lines and absorption lines, we started observing onto the photographic plate from any gas of some material, and then this was the beginning of the spectroscopic field. Then there was a development after the prism. There was some development that diffraction grating came into the picture in 19th century, end of the 19th century, and then the diffraction grating has definitely a higher resolving power than this prism, and it has been found that the line spectra, like emission spectra and absorption spectra, uh, uh, they were highly resolved spectra were started observing by that dimension. Then, in the same parallel era, there was a scientist who first showed very important aspect, that the emission, the lines, the emitted the lines, the frequencies and the absorbed frequency of any given same element, they coincide with each other, means they are the same line. So it means either you record the emission spectra or you record the absorption spectra, both are same thing, give the same information about the material. So, and one more thing he mentioned, that each element has its own characteristic line spectrum. So this was very important aspect, because of that to invent something unknown, uh, or to characterize something which is unknown in the material science. And then for the first time, what is the constituent elements in the sun and stars were started means invented. Even today, because of this spectroscopic tools and the analysis, we are able to know that what is the constituent material inside the sun and other stars, So then there was a development in 1885 when Balmer has given a series of the frequency lines in the visible part of the hydrogen atom, and there was a then thereafter, and it was he had given a very empirical formula, that experimental formula. This is the experimental formula, and based on that, that series could be explained to some extent, and it was called the Balmer formula for hydrogen atom in the visible region. But in other regions also, several line spectra were the series of hydrogen atom were invented, and these were named as Lyman series and Parsons series and Brackett series. They were not in the visible region, but they exist. You know that these were the early age experimental observations, and it was the beginning of some spectroscopic field. Then, in parallel, in the 20th century, in the beginning, Bohr has given a model of the. Then it was the beginning of the structure of the atom investigation. That what is that? So whether atom exists, so how it is stable, and then this was the thing that is going on, and then the Bohr particularly combined the three concepts of era, that Rutherford nuclear model, and then Planck's quanta, and the photons of the Einstein given by Einstein, photons concept, and he explained the existence of the atom, that what is the structure of the atom and how it is stable. So he gave the first idea that the nucleus is at the center and electron is revolving around it, and if it is around revolving around it, then how it is stable, because according to the classical electromagnetic theory, it can never be stable. And why it is not stable, you know very well, that when electron is whirling around the nucleus, it is accelerating, and once a charged particle is accelerating, it is losing the energy. Energy is released, and so when energy is lost, then this electronic energy is lost. After some time, it should be collapsed, and the atom should not be stable. But Bohr has given a model on the basis of the two postulates. The postulates you must be knowing, that I'm just reminding you. I'm just reminding you. You know all these things very well. And then when electron moves in the circular orbit, then nucleus, but in the certain stable orbits, they are not allowed everywhere. So they have a certain discrete allowed energy levels of these electrons revolving around the nucleus, and the electrons in the stationary orbit, which are said to be a stable orbit, will not radiate any energy. So it was the postulate. The energy will only be radiate or emit or absorb when the electron will have a transition from one level to the other. Then only some energy absorption or emission will be involved. So these are the two postulates of the Bohr model, and it is postulate because at that time there was not any experimental evidence. But anyway, based on that, he has given a very uh, successful thing that this was established that atom is stable. So we had to, and scientists had to accept that model. And on the basis of the classical model, I'm quickly giving you this brief background idea so that I can touch to my topic what I have chosen to cover. So these are the background things that would be needed to you for further explanation. And you see that from that model, the following important parameters were calculated related with the uh, one electron system, in which nucleus may be bigger and one electron is surrounding this nucleus. And then in that case, that's why Z is involved over here. This is the velocity of electron around the nucleus, and Z is the atomic number. And you see that this is the radius of the electron orbit, and this is the energy difference between two levels when transition takes place from lower to higher or higher to lower level. Energy either emit or absorb. It will be governed by this formula according to Bohr model also, and it is very close to, the, the empirical formula given by Palmer. And you see that from there it has been calculated a constant, and you know that this constant is calculated from our model that is found to be this is called the Rydberg constant, and it was found to be 109,737 centimeter inverse. Although it is a very close to the experimental value, but it is not exactly close to. So it was acceptable model, but this Rydberg constant was not exactly matching with the experimental. Okay, so from there, uh, the energy level of one electron atom could be calculated for this one electron system. From this formula, you see that this is the outcome of the Bohr model. And you see this is equal to minus 13.6 Z square. And when you take the hydrogen atom exclusively where Z is equal to 1, the lowest energy level is minus 13.6 electron volt. It is 13.6 electron volt is also called ionization because energy is required to eject the electron from the hydrogen atom. One more thing. This is the background idea I am giving to you so that I can discuss the topic what I have chosen. And this is another thing that I have to tell you, and you must be knowing also, but it is just a reminder to you that in atomic physics, it is very useful to introduce a very peculiar set of units. It is called atomic unit. You know that this is just to simplify your analysis so that the complicated things and formula should not be involved. And ultimately, we come back to the actual formula in the last, assuming that mass of the electron is taken to be 1. This is called unit of mass. Uh, uh, Although it has a mass, but you know that we are taking it equal to 1. Another is the unit of angular momentum, that is h cross is equal to 1. We are assuming. And electronic charge, unit of the charge, is also taken to be equal to 1. And another thing that 1 by 4 pi epsilon 0 is equal to 1, that is epsilon 0 is equal to 1 by 4 pi. So this is the assumption of the atomic unit, and we take it, so the things will be simplified, and we all calculations we shall do into the atomic unit, and ultimate result what we'll get, we'll convert it again to the TGSR SI unit. It is the Fock convention. And so if you are talking about in the atomic unit, you can see from here that if you are taking the Bohr model and the first orbit of the Bohr model for the hydrogen atom, then you see that first orbit of the hydrogen atom, the radius of that A0 is a very standard parameter. And you see that according to this convention, all the parameters have to be equal to 1. And so A0 is also 1 atomic unit. But you see that these are the fundamental units, whereas the atomic, this A0 equal to 1 is a derived kind of thing. So it is not fundamental, but it is derived. And you know that energy, you have seen that previously, the energy formula is this one. It's a bigger one. But here in atomic unit, it will be reduced to minus Z square by twice n square. And so, just to simplify it. So you see that in the hydrogen atom, one more concept I would like to give you, that in the hydrogen atom, velocity of electron in the first Bohr orbit is given as E square by 4 pi epsilon 0 h cross. You can check it. This is very basic for you. But once we are talking that velocity of electron into the orbit, then it can be written in terms of the velocity of light. So a factor will come, and that is called the alpha. And so this alpha is known as fine structure constant. This is a very standard nomenclature into atomic physics, and you must be knowing about it. So in atomic unit, you know that from here, if you put these fundamental units from here, then it will be equal to 1 in atomic. And so alpha C will be equal to 1, and so alpha is equal to 1 by C. So you will see, and it is equal to 1 by 137 in atomic unit. You can find it out. And then you see that in our further discussion, we will always use, not will use the velocity of light everywhere. We shall use this alpha in our formula and discussion in terms of fine structure. Okay, so this is the background thing what we have already discussed. And so what we shall do that, I would like to come to some actual topic. And the actual topic is this, that I will go to my notes, what I have written by my hand. And I suppose that it will be very visible to you. So let me give me a moment that I will start that one. So I am minimizing it, and I am starting this my notes here. Yeah. So the notes I have written by my own hand, and sometimes
Sir,
it may not be
sir?
good to you. Yeah.
Sir, if you want to show your this thing, you have to stop sharing the first one. Just
Okay,
minimizing
okay.
will not help.
Okay.
So you have to start
Okay.
sharing again and again show. I mean, choose that particular window where your handwritten.
That's right. That's right. Yeah. So I'm. It is showing that it is a new share, something like that.
So you have to stop sharing first.
Unless, well, I'm taking the help of my one boy that who is helping me. That
No
how
problem,
to stop
sir.
it.
You have to first stop sharing.
How to
Then
stop. So I have stopped it, and
now once again click at share screen.
And then okay.
Then again
So,
choose a window, and your handwritten note should be already visible on your screen. Then you have to select it.
Okay. So I will go to the application window, and I'm doing it, and then I'm sharing it, and I think that it should be visible too.
Yes, sir. Now it is visible.
Yeah, is it? Okay.
Yes, sir. Very clear. Very clear.
Yeah, yeah. So, students, I'm sorry if you are not able to see this, able to read it very clearly, but I'm telling you line by line so that Anas, ये कैसे हटेगा? ये green color कैसे हटेगा ये? Yeah, it's okay.
So your handwriting is quite legible. It's no problem to read.
Thank you. Okay. So, in continuation of my previous discussion, what I have placed before you, and it was really very basic, and that basic few reminders were necessary because when we come to the actual discussion, it will be very useful. So you see that I have written here that is atomic physics quantum mechanical approach. You see that if we do any problem which is related to the atomic physics, why we immediately come to the quantum mechanical approach? That is very necessary to know, and you must be knowing from different corners that when you see, yeah, hello. So it is a quantum mechanical approach. So why it is necessary to quantum mechanical approach? Because you know that in the atomic level, the order of the size of the particle is very small. You know that the order of size is the angstrom order, and so whenever the particle size is very small, then it is a quantum mechanical approach. And you know that in the atomic physics, in the classical physics, you will find that several things and several observations experimentally what you got, it was not very explainable to the classical physics, and Bohr model was based on the postulates, and certain things were acceptable, and certain things like Rydberg constant, I gave you the example, it was not the exact matching. So quantum mechanical approach is very important. Secondly, once these small particles of the angstrom order, when they are moving in the orbit, their speed is uh, so high that sometimes we will start from the non-relativistic approach first, and then we'll find again that this non-relativistic approach is not enough. So that's why um, this quantum mechanical approach and the relativistic thing will come in. So let me start from the very basic, that the simplest atom in the atomic physics was taken to be the hydrogen atom. And hydrogen atom, because it has one proton and one electron, let us start from here. And then this atomic physics goes to two electron system, then it goes to many electron system, and you will see that how the complications are, it becomes critical and complicated as the number of electrons increases in the outermost orbit in the orbit. So let us start with the simplest atom. So one electron system is not the only hydrogen atom. You must be knowing that there may be some other kinds of atoms and ions which also has one electron in their orbit, like deuterium, like tritium, like you can take helium, one electron dragged off from there, or lithium, two electrons dragged off from there. So nucleus would be the same, having the Z atomic number, but you can force it to have one electron in their orbit. So such kind of systems are hydrogen-like, and that's why it is called hydrogenic systems or hydrogenic atoms. Okay, so let us start from the very generalized kind of one electron system, that is the hydrogenic. We are starting from here. So you see in the quantum mechanical approach, what we do generally for any system we have, whatever the quantum mechanical problem we take, we write a Hamiltonian for that. And for writing a Hamiltonian, we know that there is a kinetic energy part. We simply write E square by 2m. And then we write potential energy. So finding out the potential energy exact term, that is important in framing any the Hamiltonian. So Dirac said once that once you are, for any system which is simple or complex, once you are able to write the Hamiltonian exactly, then your half of the problem is solved. So Hamiltonian, we have to write. Then in order to write the Hamiltonian for one electron system, what we do, that we check this system, that we have a nucleus here, one electron is there a distance apart at r distance, and it is whirling around the circle. And so the what will be the Coulombic potential? It's a very simple in a SI unit, that is minus Z square by 4 pi epsilon r. And so a very once you know the Coulombic potential, that one Hamiltonian can be written, that is p square by twice mu plus the potential, that is p square by twice mu minus z square by 4. So you have framed the Hamiltonian, and you know that why mu here, because mu is the it is called reduced in the form of small m, m, and m plus capital M. The capital M is the mass of nucleus, and if we assume that mass of the nucleus is quite large as compared to mass of electron, infinitely large, then this reduced mass will be close to the mass of the electron. So we can easily replace mu with the mass of electron without much error into the Hamiltonian. But anyway, so we can write very easily. That is one body time independent Schrodinger equation. Much you already know that this is the kinetic energy part, the potential energy part, and psi r equal to. Now, once you have framed the Schrodinger equation, then the quantum mechanical approach is this one only, that for any given system, you write properly a Schrodinger equation with a suitable Hamiltonian and then solve it. Schrodinger equation, wave equation, differential equation, you have to in the Cartesian coordinate, and you have to solve it. And solve it means that you will find two solutions. One is the energy eigenvalue, and other is the eigenfunction. IR eigenvalue will give you energy value, that is whether it is discrete or continuous, it is the outcome of the system. And the wave function, you can find it out, and wave function will give you the probability of finding the system in which state that it will be given by that. So this is the approach. In the one electron system, once you have written the Schrodinger equation in the Cartesian coordinate, of course, it will be very difficult to solve it into Cartesian coordinate. So your quantum mechanics teacher may have already told you that there is another system. It's called the spherical polar coordinate, through which this Schrodinger equation can be solved, which is called the method, which is separation of variable, in which this wave function is a function of x, y, z. It can also be written as a function of the spherical polar coordinates r theta phi, and so it can also be from the separation of variable. This wave function can be written as a product of the two wave functions. One is the radial function, the function of r only. Other is the angular function y, which is the function theta and phi. You know, these things I'm not going to discuss much because it is the part of your quantum mechanical teaching, and you have already learned it. You have already learned it. It is just use of this quantum mechanical approach in the atomic physics. Okay, so I am directly coming to the eigenvalue, what it can be obtained from this solution of Schrodinger. And you see that it is equal to minus half 2n square, and this kind of expression you will get it from this solution, and you are looking at that it is a similar kind of the outcome you are getting what we have got through the other empirical relations, or the empirical analysis, or the semi-classical approach, also similar kind of energy value. So you know that one atomic unit of the energy is equivalent to m e to the power 4 h cross, and its value in erg Celsius unit and in electron volt, it is 27.07. So this is also obtained from the quantum mechanical analysis. And in atomic unit, you can write this energy value where we are assuming the mass of electron, mass of the electronic charge, and h cross equal to 1. And it is En is equal to minus z square by twice n square. Okay, so there is another unit which is necessary to tell here so that we can discuss further, that this is another unit which is called Rydberg. It is simply that the same expression what we have got earlier, it can be written in this form. This one can be written in this form, and so So 2 we are taking inside, and so this value is taken to be uh, uh, equal to 1. So in the Rydberg, the energy value is written as minus z square by n square, means that 2 you are taking inside, and so the 1 Rydberg of energy is equal to half of the 1 atomic unit of energy, 13.5 electrons. So these are the some units which are frequently used in atomic physics. And you see that this is also a very discrete value. It is depending upon n, and you know that n is a principal quantum number. We shall talk about it later. And when n is equal to 1, E1 is equal to minus z square. Rydberg, it can be written in the form of atomic unit also. So these are the discrete values when n is equal to 1. Allowed values of n is equal to 1, 2, 3, and so different values of energy you will get. Okay, so as far as mm, the other solution is concerned, that is the for one electron system, that is the wave function. And wave function, if we are talking in terms of the complete r theta phi and in the form of the NLM, then it is a complicated wave function in the form of some legendary polynomial and all these things. So it will not be used over here. And we shall not use it because it is your quantum mechanical problem you have already learned. But I can remind you here that if you are taking the hydrogenic system, then complete normalized hydrogen wave function for the ground state of hydrogen atom can be written as this expression, what we shall use time to time. This is the wave function psi 100. It is equal to 1 by under root 2 pi, and in terms of z, and a0 means the first Bohr orbit, we can write it. And so this is the ground state. But you know that from here, using this ground state wave function of normalized hydrogenic wave function, then we can find something like I have noted here the one question for you. The question is, find the size of the hydrogen atom in the ground in its ground state. Suppose you have a hydrogenic atom, one electron system, and then if you want to know what is the size of that, means that you have to find it out. The at the ground state means that you have to use this wave function, and using that you can find it out what is the expectation value of r. I'm sorry that I have written r. I should have to write here r, so I will correct it later on. Here it should be r. And so the expectation value of r with psi 00, psi 100, psi 100, or it can be written like this also. So okay, by mistake I have written this side here. Then in integral form you can write like this. You must be knowing that what is the meaning of dqr. Dq bar, that is the r dr sin theta d theta and d phi. So in the angular form and this in that also. Once we integrate it, then psi star r psi r dq bar, then you know that since it is a ground state 100, so psi star and psi is the same thing. So we shall integrate it in this form, and finally you will do that. You will integrate it, and this part you will find that d phi 2 pi, it will be 2 pi 0 to pi sin theta d theta, it will be equal to 2, so it will be 4 pi, and 4 pi we shall write over here and then integrate here, and then this integration can be done from this integration formula. And you know that this gamma n plus 1 alpha to the power n, where this is alpha. Here in this case 2z by a0 is the alpha here, and so from here we shall find it out. The size of any hydrogenic atom is 3 by 2 a0 by z. You see that this hydrogenic atom is depending upon the value of z. So if it is exactly mm, hydrogen atom, that is one proton, then Z will be equal to 1. And according to the Bohr model, the size of the radius is A0, then size of the hydrogen atom should be 3 by 2 A0, according to this Schrodinger equation and RU quantum mechanical. And you see that this value will be depending upon the Z very quite enormously, that if your hydrogen atom, then of course it is 3 by 2 Z, A0. But if helium, then it's 4A0, means that if the value of Z atomic number is increasing, that is, for example, iron, if you are taking Z is equal to 26, and if it is increasing, then size of the hydrogen atom decreases linearly with respect to the value of Z. So size reduces and reduces, you see. So you know that I'm not going to do the details of that how it has been calculated, but for general hydrogenic eigenstate, you see that for psi NLMR means that this is not for the ground state, it is for other states also. Then you see that this R and LM can be calculated. That is the size of the hydrogen atom when it is not in the ground state. Then you will take the generalized wave function, and in that it has been calculated. And you see that the generalized wave function is can be the product of the radial function and the angular function. And for calculating this particular aspect, the size of the hydrogen atom, the radial function is enough. And so, using that simplified version, we can calculate it, and then we find this size in terms of A0 n square by Z 1 plus this formula. So from this formula, for any excited state, means that for any value of n and L, you can find it out that what is the size of the hydrogen system particle. Okay. I think that for students it will be very useful that instantly they are able to write this integration also, because these integrations will be used in your analysis when we shall discuss about the fine structure, and then it will be very much. And so if you are able to write in somewhere in the notes, then when I shall discuss to you further, it will be useful for you. So I'm keeping it for a moment over here, and so please you note it down. These integrations through this psi NLM, it will take quite a long time and it is not the atomic physics problem also, it is a quantum mechanical problem. So this is the outcome what I'm taking directly. Okay, yeah. So I think that you may have noted it, and then I'm proceeding. And with this background idea that this all non-relativistic approach of solving the one electron system and various parameters, you can note it down, but it is a non-relativistic approach, and relativity is not coming in till now. So we thought that through this approach the problem may be solved, and whatever the spectral lines are observed through this quantum mechanical approach, taking one example, we can see that our problem is solved. But at one place we are always stuck. You see that why we are keep on discussing once this non-relativistic approach is enough. So, but you may be knowing that for this system, for example, if we compare the Rydberg constant, the Rydberg constant experimental value is noted experimentally, and from Bohr's model, the value was quite close to the experimental value. From this non-relativistic approach, also we have found the Rydberg constant, and which is very close to the experimental value. But it is close to the experimental value. It is not the exact. So that's why the scientists are not fully satisfied that something more uh, is to be done to find out the exact Rydberg constant. This was the one aspect, and other aspect I shall discuss about you. That's why we are keep on discussing on to this atomic case, but even in the one electron system. So before I go to that aspect, let me discuss one more important thing called the degeneracy. This is a very important. Sometimes, or most of the time, we talk about the degeneracy, and that is the uh, thing that we can start from here. One very striking feature may be noted by us that expression of energy we have repeatedly getting it is equal to En is equal to minus Z square by twice n square. So it is only depending in the atomic unit, or even if you are writing it in CGS or SI unit, it is only depending upon the uh, principal quantum number n. And so the energy state is, it means that if you know the principal quantum number n, but once you know the principal quantum number, there are other quantum numbers which are for a given value of n, their numbers are more. It means that for any given energy level, there are other states also that should be, and that is called the uh, degeneration. Means that for any given energy state, there should be different states, quantum states, what is means where the system would lie. And so that is called degeneration. For example, I am taking you for a given value of n, the L varies from 0 to n minus 1. And for a given L, the magnetic quantum number ML varies from minus L to plus 12, passing through the 0 value. And so it means that for a given value of n, so many other quantum numbers on which the wave functions depends, and so quantum states of the system would lie. And that's why if we talk about the degeneracy, the total degeneracy of the level En can be written as this formula, that is from L0, L is equal to 0 to n minus 1, that is twice L plus 1, and that can be further expanded. You see that 2 L is equal to 0 to n minus 1 L, and plus L is equal to 0 to n minus 1 equal to 1, and so further expanded like this, and finally it will be equal to. So if energy En is given for a given value of n, the degeneracy will be n square. The n square number of other possible states will exist. So it means that when n is equal to 1, then state is 1. You can see that we have already learned in chemistry and physics. That is n is equal to 1 is equal to 1s. And when n is equal to 2, the 4 states will also lie, and these are, we have already learned that 2s is equal to 2p, 2p0, 2p. And when n is equal to 3, then 3s, 3p, and 3d, 9 states will exist. So and so on. So this is called degeneration. One more thing in spectroscopy, once you will go to the 2-electron system and the many electron system, there is one thing is very important, that that is called the spectroscopic term symbols. You know that electron have energy which is depending upon the principal quantum number n, but electron has different angular momentum, like orbital angular momentum, there is spin angular momentum, and there's some j value, total angular momentum. So these parameters are also associated with this spectroscopic term for the electronic state. And so for one electron system also, you see that in one electron system, you have only one electron. And so it will spin. So there is no question of whether it is spinning clockwise or it is spinning anti-clockwise. There will be only one state. But if you have two electrons, then how these two are spinning? One is clockwise, other is anti-clockwise, and both are anti-clockwise, both are clockwise. Something like that. These are the different permutations. But in one electron system, only one thing, that it is spinning. So its value of S will always be half. But anyway, there is a method of writing the spectroscopic term symbol, so that by writing a particular term, you can get to know the state and energy of that system that that moment only. So that is always written for one electron system. That is written in the form of this n bracket twice s plus 1 L j. Now I will explain that for one electron system, we know that in which orbit it is orbiting. That's what which energy level it is given. So it is the value of n. But this n we always don't write in the case of two electron system and many electrons. Okay, so the term is this: the central part always represents the orbital angular momentum. Orbital angular momentum, L, and this here in this part, this is twice s plus 1. This is representing the spin. So in one electron system, s is always half, and so 2s plus 1 is always 2. And so actually it will be more clear if you go to the many electron system, multi-electron system, then what is the meaning and significance of 2s plus 1? It is actually called multiplicity. So when spin will come into the picture, then it will be discussed. Here, single electron system. So this is not very important, but term symbol is written in this way. And this is the total angular momentum, J. J is the total angular momentum. Okay. And so we can give the example that suppose one electron in the 2p state, then how to write the term symbol? That is n is equal to 2, and p state, so means L is equal to 1, and S is half, to 2s plus 1 is 2, and so J is L plus S, and you know that J, so S, it will always be L plus S or L minus S. Two possibilities are always there. So you know that it can be written in L plus S or L minus S. So value of J will be either 3 by 2 or half. And so for 2p state of electron, it will be written two term symbols, one like 2, 2s plus 1, p 3 by 2. And the same p electron has another state, that is 2, 2p and half. So the p electron, p state electron, the term symbol will be written in 2. Like in d electron, one electron system, 3d if you have, then 3d2, 2 always be there, twice s plus 1 single electron, so it is always 2. And then central part will be d, that is the d orbital electrons, and then 5 by 2, j will be 5 by 2, 2 plus half or 2 minus half, 3 by 2, like 4, like this, 2f 7 by 2 and 2f 5 by 2. So for one electron system, things are very simple, and one electron system, in that you can write the term symbols very easily. But as soon as you go to the two electron system, there are various other parameters, various other constraints, but the variations will come into, like spin and like many things, and so things become complicated there. But it is the beginning how to write the term symbol. Okay, but symbol is important in spectroscopy because this one expression gives you a lot of idea about the individual state of the electron and the energy. Okay, yeah. Well, so you see that till now in one electron system, Punita ji, are you there? Hello?
Yes, sir. Yes, sir.
Are you there getting bored? I have further how much time,
Yes,
that
sir. Half an hour. It's 6 o'clock
half an hour?
now. You have half an hour.
Half an hour, yeah, okay. Okay. Well, so till now I was really in the background of the idea that atomic physics and mostly to one electron system. And the approach was that how the things were moved from the classical approach to the quantum mechanical approach and Schrodinger equation for one electron system, how to write and solve it. Several things can be done, but yes, it was really a recapitulation. Actual topic I am going to start now, that the one electron atoms, the one electron system, in which we are talking about the fine structure. Okay, what is the meaning of fine structure? I would like to explain first that why this is fine structure is required, and what is the problem till now. What we discussed, what is the problem till now? So actually, in our previous discussion, you have seen that energy levels and wave function of one electron atom was based on very relativistic, non-relativistic. Sorry, it is written something wrong. Not relativistic, non-relativistic, Hamiltonian, and it was simple that H is equal to P. It is also non-relativistic, and this part potential energy was also electrostatic, non-relativistic the potential energy. You see that what was the discrepancy or problem till date, till now, that in parallel to the these theoretical models and various explanations, the experimental development was also very fast. And experimental development means what kind of development? Means that to see these spectral lines, various spectrometers were developing in parallel as the models were developing to explain the phenomena. And it has been found that high resolving power spectrometers were coming to the market, coming to the scientific field very continuously. And so we were able to see these spectral lines through the modern spectrometers, and we found that the spectral lines what we are getting, they have certain structure. It is not simply a line spectra, very fine. It has some structure. Means that experimentally we have started finding that theoretically what is the calculation through this non-relativistic approach, it is not exactly lying on the same line, same point, same line, what it should be observed experimentally also, but it is not. So we found that some shifts, some splittings into the line very clearly. For example, you must be knowing that even with the very simple spectrometer, the D lines of the sodium, yellow lines, D1, D2 line is splitting. With this very good spectrometer, we are able to see this D1, D2 line quite apart, and we are physically very apart. So, like that, several spectral developments came experimentally, and we found that these spectral lines are having some structure shifts and splitting. So, it means that there was a need of the corrections into the Schrodinger equation, and there is a need of correction into the Hamiltonian in quantum mechanical approach. And so the first thing was introduced that instead of non-relativistic approach, let us explain, or let us try to find it out, what is the correction. So non-relativistic Hamiltonian was H. So if we approach is towards the relativistic phenomena, then some correction factors are required to be, some correction terms are required to be added to this H. So what are those correction terms? So there is one thing, that is kinetic energy. There may be some corrections in the potential energy. There may be some corrections, or something what we are not considering into this Hamiltonian, something which is not the part of this Hamiltonian. Till now, conceptually it should be, but it is not there. So there are three types of corrections. Now I'm summarizing. Kinetic energy correction in Hamiltonian. The second is the corrections into the Hamiltonian which will be added. That is the spin orbit interaction, what we have not yet considered. And third one is the correction in potential energy. And so one by one, I shall discuss with you briefly, and then proceed further. So let me start with the this energy level shift or corrections due to kinetic energy correction, which is also called very popularly, that is called the mass correction. And you see, if we start from the very basic approach of relativistic approach, that is, what is the relativistic kinetic energy? You can very write it that relativistic kinetic energy is equal to relativistic energy due to motion of the electron and minus rest mass energy. And so with this simple thing, if you write it, the expression, then it is equal to p square c square plus mg square c square. This is the relativistic energy due to motion under root and minus rest mass energy. And then we have to expand it. So for expanding, when we are expanding like this, then after expanding this term, first term will be cancelled with the rest of the energy, and this is the relativistic kinetic energy. So the first term, p square by twice m0 or twice me, mass of the electron, and you see that this is the same as used in TPS non-relativistic approach, and this is the first order correction term, and the rest will be second order correction term, third order correction term. And it has been found very simply that first order correction term is enough to simplify the or to obtain the fine structure in the kinetic energy, and it is enough that contribution is quite large as compared to the second order and third order correction term. So let us concentrate on to this first order correction term. So you see that the old Hamiltonian, we see it again, it is sum of the kinetic energy T0 and plus V, and kinetic energy T0 is equal to H0 minus V. And so the correction terms, if we are writing it, just we are making a manipulation and rearrangement, and then after rearranging, you will find that this can be written in this way, taking it out, and p square by twice m0 and that's square, and it can be written in terms of T0. You see that non-relativistic kinetic energy divided by 2 m0 square, and so T0 can be written as H0 non-relativistic Hamiltonian minus V square and divided by twice m0. So this term is taken to be a relativistic correction H1 dash into the kinetic energy part, or so to the Hamiltonian. So this is the correction term, and because of the first order perturbation we are taking. So the energy shift because of this H1 dash, how much energy shift because of that non-Hamiltonian, this is non-relativistic H0, you find the energy En. It is equal to minus Z square by twice n square atomic. But because of this this correction term, you see that how much energy is involved, and so it will be a shift. So very simple approach into the quantum mechanics, that because of this Hamiltonian, you take the expectation value of that and then calculate this energy value corresponding to that, and that will be the shift into the energy because of this relativistic mass correction. Okay, and so delta E1, that is, this is the energy due to delta H1 dash. Take the expectation value. You can write it like this, that you are putting it this whole thing here and then the whole thing here, and you see that 1 by twice m0 c square, if you are taking it out, this can be expanded, and 1 by 1 you can find it out, and then you shall see that because of the value of energy will come n square, of course, expectation value, and then because of this h0, 2 can be taken out, 2 en, then this v expectation value of that, and v square expectation value of v. So main task is now this, concentrated to this, that find it out, this v and this v square average value, and so one by one we can take it, that the average value of this v will be equal to, you know that the v is z square by r, and from here z square can be taken it out, and that is concentrating to 1 by r. You know this, I told you that you noted down the three values, 1 by r n lm generalized. And so 1 by r n lm, what you have noted from there, if you use it, that is equal to z by a0 n square, and so this value will come here, and in atomic unit v is minus z by n square. In the same way, the expectation value of our average value of v square can be calculated from here. Here 1 by r square will be involved in lm, and you can write it the formula like this, and so delta E can further be expanded in this way, and so you can find it out that delta E1 can be written in this way. Okay, where En is equal to minus z square by twice n square in atomic unit, you have already found it, and then you can write further manipulation and rearrangements. You see that we have already told you that c is equal to 1 by alpha, alpha c is equal to this one, we have already discussed earlier, and so this can be delta E1 can be written in this way, and after the further uh, uh, further reduction, you'll find that instead of c square, you can write it alpha square z to the power 4 twice n to the power 4, and further simplification. And so final formula, this is in atomic unit. Same thing, you can write it into the Rydberg just by getting rid of 2 factor here, that is minus alpha square z to the power 4 and n to the power 4. This formula will come, and so ultimately you can write. Then you can see one thing is very important to note, that delta E1 is the shift into the energy what you have got because of the non-relativistic approach, En. So from En there will be a shift on the negative side, and this can be numerically calculated from this formula, and the shift is depending upon not only this principal quantum number, it is also depending upon the orbital quantum. Okay, so you can see that this is the one of the fine structure and shift into the energy level you can calculate and compare with the experimental value, whether how much it is close to the real experimental value what we are getting. So this was the one correction into the Hamiltonian and mass correction, and this is the one energy shift you have got into the energy once you are including this. Okay, now we shall talk about very another important thing, another correction. Another correction is the spin-orbit interaction. You know that I would like to give a very brief explanation that suppose you have forgotten it, and I am just reminding you once again that what is the meaning of spin-orbit interaction. In the same atom, one electron system, suppose you are talking about, then what do you mean by the spin and orbit interaction? You see that you visualize that one electron is revolving around the nucleus. It is orbiting into a circular orbit. You see that once electron is orbiting, moving in a circular orbit, which is a current. And once you know that once electron is moving, it will generate a magnetic field. Okay, so this is magnetic field is generated. Now electron is spinning also. So electron is spinning in its own magnetic field, and you know that once it is spinning, it is another kind of movement or motion at its own axis. So if anything is moving at its own axis, means it will have a magnetic moment. So
Sir, we can't hear you. Hello.
Sir, sir, we can't hear you. You are muted, sir. Hello. Sir is no longer the co-host. Hello. Dr. Parul. Dr. Parul?
Ma'am, now he is co-host.
Yeah, sir, we cannot hear you. You are muted. Please unmute your mic. Hello.
now it is okay.
Yes, sir, it is okay. Thank you so
It is
much.
okay.
Yes.
How it happens that in between sometimes it happens?
It so happens, sir, we have renewed the subscription of Zoom yesterday
Okay.
for the third month. So maybe today being the first day, it is switching a co-host to normal participant automatically.
Okay. Okay.
So it is happening.
So, Dr. Punita, how long I was mute? I'm not aware because
only 1 minute. Only 1 minute.
only one. It is okay. So I'm starting it again.
We are attentive, sir.
Sir, there is one question also.
Yeah.
Pallavi is asking, is it that both B and H are similar?
What?
B
Is
and H.
Pardon?
B and H, are they both similar? This hint
Let
that
me
you have
come to
written.
my lecture first. Then I'll be able to recall
Yes,
it.
sir. Yes.
Yeah.
Okay. Okay.
Okay. Let me, because it is stop sharing, so I have to start it again. So.
Sir, we can see your screen.
You are able to see that?
Yes, sir. Hint, electric field experienced by electron. E bar is equal to ZE by R square.
But on my screen, something is going wrong, that it is not moving. Anyway.
Okay, sir. Then you can stop sharing and start sharing again.
Again. Stop sharing.
And share
then,
again.
Yeah. Now it is okay?
Yes, sir.
It is okay. Okay. So what was the question, ma'am? Can you?
Yes, sir. One student is saying, is B for Bombay? I mean, B for magnetic field, obviously. B and H, are they both similar? And another student is saying, if you could kindly repeat page number 10.
Page number 10. Okay, okay.
That's all, sir.
Okay, okay. This is page number 10, probably. Yeah. So I have to mention something again to you. about page number 10. Let me reply first that what is the difference between H and N. Actually, once we hello.
Yes, sir.
Okay. Once we give that, you know that in the intermediate book it is written that H is the CGS system. When once we give the analysis in CGS system, then H comes in, and once we go for the SI system, then B is come. So here H and B has no difference. We mean to say that both are the magnetic field, and one is called the magnetic induction, another is called the magnetic field intensity. But in both the system of CGS and SI, this is valid equation. Okay. As far as this page 10 is concerned, I am repeating it once again, that you know that from this you have seen this equation and delta E1, and this is simply a simplification, plus and minus, and from here you can come to this equation, and here we are taking C square in the numerator as alpha square because C is equal to 1 by alpha. It is a finite structure splitting term, and it is alpha square, and then Z to the power 4 we are taking common, and then this is a simplification, and in atomic unit you can write this energy out of this correction. This is the shift into the energy because of the kinetic energy correction. This is in atomic unit, and once you are taking rid of these two factor, then it is converted into Rydberg. The relation between atomic unit energy and the Rydberg energy is this much only. Okay, I think that there should not be any problem, and then I should go ahead. Hello, hello,
Yes, sir.
hello.
Yes, sir.
Any problem? I should go ahead.
Yes, sir.
Yes, sir.
Okay, okay. So you see that in spin orbit interaction, either you talk about V or you talk about H, both are the similar thing, and then you can write it and both mu S and the there is I think that somebody should mute, and that's why some echo is coming. Okay.
Ansi, please mute yourself.
Yeah, yeah. So the magnetic field of the electron experiences when it is in orbit, electronic orbit, then magnetic field or H can be written as this. And so how how we have got this form expression, this is the hint here given. You know that electric field experienced by electron is written by this expression, Z square by R square, and then B is equal to BRH, of course. Once then V cross E by C square, and from V square, you know that L the orbital angular momentum is equal to m0 R into V, and from here, if we both of them are um, uh, combined, then this magnetic field can be found in this form of the expression. Well, so spin orbit interaction means that interaction of the spin magnetic moment and the magnetic field. And so if we write in the form of the dot product, then this H2 dash will come into the picture, and that will be equal to Z square T square by M0 C square R cube L dot S. So orbital angular momentum and spin angular momentum, they are the dot product are involved into this correction term. So what I mean to say that well, this factor of half comes because you know that in the orbit when electron spin, there is one kind of precession is there, and which is called Thomas precession, and because of this Thomas precession, this half of the factor comes in. I don't want to go to the details of that, but this factor is the final one, and there L plus L dot S will be involved over here. Uh, this is very important factor over here in this spin orbit interaction. So the H2 dash, that is the correction into the Hamiltonian because of this spin orbit interaction, because once you are taking in one electron system, there will be spin orbit interaction, and we had not included into the Hamiltonian, and because of that some shifts or some splittings are also possible, and what we are getting from the very important spectrometers, very advanced equipment. So you see that if this correction factor is also involved, so from the expectation value of these, we can find it out. The shift are splitting into the energy levels, and because of this these factors, and you see that we can find it out the expectation value of this H2 dash correction, and for that we can use over here this method, that some of the factors, that is the half z square by this m0 square c square will be taken out, and inside it will be 1 by r cube s, and main task is this, how to find this expectation value. And so we will start from here, that total angular momentum J is equal to L plus N, we already know. So J square can be written as L square plus S square plus twice L dot S, and so L dot S can be written in this way also. And so if you put it over here, then this will be the average value will be expanded like this, and many things we know now. The expectation value of J square is in terms of the quantum numbers and in terms of their values, J into J plus 1 total angular momentum h cross square, s square expectation value L into L plus 1 h cross square, and s square will be s into s plus 1 h cross square. So with this background, if you put all these values here, then we have I told you that 1 by r cube will be used also. From here, the expectation value of 1 by r cube, we can note it down from your previous slides, and then in atomic unit, this delta E2 will be written with this expression. Okay, and so in atomic unit, if you write, several things will be equal to 1, and so it will be simplified to delta E2 minus alpha square z square and this much formula. So this is the formula, and this is the expression for that. And so in terms of the non-relativistic energy, if you find this delta E2, then this is the expression for that. You see that this correction, or this energy value due to this spin orbit interaction correction, you can find it out that this energy is not only dependent the value of n, it is depending upon L, and it is depending upon J, and it is depending upon J means it is also some sort of, it is depending upon the value of the spin value half. So whether it is L plus half or L minus half. So you see that one thing is very important to note it here, that, and I'm going to close within 1 minute, that this expression is not valid for L is equal to 0. This expression, that is delta E2 or spin orbit interaction, it is not valid for L is equal to 0. L is equal to 0 means S orbital. S orbital is highly spherical, you know. So this delta E2 is not valid for the spherical orbit. It is only valid for the orbital like E, D, F, other higher orbitals. And why it is so? Within a half minute, I would like to explain that this expression, why it is not useful or it is valid for the for this L is equal to 0, because of this. You concentrate onto this correction term. When small l is equal to 0, then you see from this formula, l is equal to 0. So this capital L will also be 0. Angular momentum will also be 0. And once this angular momentum is 0, this correction factor will be 0. So mathematically also, conceptually also, that this expression or this energy shift or splitting or spin orbit interaction as a whole is not valid for s orbital, not valid for L is equal to 0. So I think that for today I have covered so many things in 1.5 hours, but definitely I commit that once I'll finish these corrections, I'll do few numerical problems for your convenience. And today I'm closing with the permission of Dr. Punita and other organizers. Yeah.
Thank you so much, sir.
Yeah.
Thank you so much, sir.
I would like to, I would like Dr. Punita that after closing this, if you can tell me on phone that if you can give me some feedback about that, I will definitely try to improve next day and next to next day. Yeah.
Sir, the students will give feedback at the end of the lectures at 8 p.m. and I will forward you
Definitely,
that.
but I
But
need
sir,
your feedback
yes,
so
sir.
that I can improve. Yeah.
No,
Yes,
no,
and
sir.
sir,
Sir,
thing is,
you're getting so many compliments. And I must say one thing, you have a very beautiful handwriting.
yes, he's got a very beautiful handwriting.
Thank
There's
you.
no doubt about it.
Thank you very much. Thank you very
And
much. Yeah.
and let me
Yeah.
pay you at least one compliment, and that is not one. I want to give many, and that's the meticulous way in which you have given a complete revision in just 1.5 hours, and also made one feel that yes, we can go ahead and start talking about one electron atoms and how quantum mechanics is engulfed by atomic physics to explain every concept. This is indeed very beautiful in such a short time. So I thank you a lot, sir,
Thank you
and we
very
are
much.
grateful. Look forward to other sessions of yours in the coming 2 days. Thank you, sir.
Thank you, sir.
Yeah. Yeah. Okay, man.
You
Thank
may
you very much.
kindly
Thanks a lot.
stop sharing your screen so that we can
Yeah.
start
Yeah.
the next
Yeah.
session.
Yeah.
Thank you, sir.